Well, welcome to the Qualcomm Institute, California Institute of Telecommunication and Information Technology, and most importantly, the Arthur C. Clarke Center for Human Imagination. I'm Sheldon Brown, the director of the Clarke Center, and I'm glad you all could join us for this midsummer musing on our place, on what our place in the universe might be, this just kind of came together out of the confluence of a visitor coming to town and some recent results that one of the scientists in the Clarke Center has been recently involved in, and it connects with another writer in residence of the Clarke Center, work that he has done and looks into about the questions of what the universe itself might actually consist of. And as we're doing this, it reminded this whole subject of the multiverse reminded me very much of something that has a bit of a deeper history, a literary history to it. And that is this story by the Argentinian author Jorge Luis Borges called The Library of Babel, which is a story written in 1941. And I don't know if any of you are familiar with it, but I'll just give you a bit of a synopsis of this story. And as the evening unfolds, you'll kind of see the connection, I think, to the subject. But in this story, Borges describes this vast library containing all possible books, which would consist of 410 pages and any arrangement of 25 alphabetic symbols in the book. And in this library, there's no two identical books, but every possible book written in that format is theorized to exist. And Borges creates a structure of this library that's these hexagonal shelves, and he stipulates how many shelves are in each room, how many books are on each shelf, and then ends up describing this is the setting and subject, and what societies develop in this context as they seek to understand the nature of this library they're in. In fact, the statement that it contains all possible books is a theory about what the library is. So they create these kind of theories to try to understand what their universe is and then what it might mean. And I'll just read you maybe a couple of little quotes from this story. When it was announced that the library contained all books, the first reaction was unbounded joy. All men felt themselves the possessors of an intact and secret treasure. There was no personal problem, no world problem, whose eloquent solution did not exist somewhere in a hexagon. At the same period, there was hope that the fundamental mysteries of mankind and the origins of library and time itself might be revealed. Those profound mysteries can indeed be explained in words, and if the language of the philosophers was not sufficient, the library would surely possess the extraordinary language required to explain these things. But this unbridled hopefulness was succeeded by a similarly disproportionate depression, as the generation-spanning investigations could hardly turn up a book that was anything more than gibberish. In his lifetime of searching, the story narrator found only two phrases of coherency. One was combed thunder, and another is the plaster cramp. So the story sets up this evocative scenario, I think, which has been reinterpreted over the years, first as a metaphor for the process of writing, how meaning could possibly be created out of what is otherwise just an infinite possibility of nonsense. The second is it was seen as a prescient tale about the nature of information and the creation of the internet. So you often found this story being rolled out throughout the 90s and in the early 21st century as people were really understanding the magnitude of what this new information system was. Now we might see this story and its narrative as a reflection of some of the latest discoveries and theories regarding the origins and the possibilities of the universe itself. And so out of this, the fact that in this multiverse we consist in, ponder this for a moment. There's this exact same lecture going on right now, except in that one, I'm wearing a yellow shirt. It's kind of mind-blowing, I know. So tonight, we're going to hear from 3 people discussing the idea of the multiverse from perspectives of current scientific theory, and with a nod to its literary merits. In part, this is due, and in part we're having this also, we're right now at the Clark Center, we're also hosting the Clarion Science Fiction Writers Workshop. And so participants from that workshop are here with us tonight. And just to give you a bit of a mention about what Clarion is, it's an intensive 6-week summer program focusing on the fundamentals particular to writing science fiction and fantasy stories. And it's one of the premier training grounds for aspiring writers of science fiction, fantasy, and horror. Right now, the instructors are Anne and Jeff Vandermeer, and tomorrow they'll be giving a reading tomorrow night at the Mysterious Galaxy bookstore. So it's a great chance to go and meet with them. I also want to have some thank yous for people who helped make this event possible. I want to thank Viasat, who is the founding partner of the Arthur C. Clarke Center for Human Imagination. I also want to thank our patrons and Founder Orbit members, Cindy and Mark Dankberg, Stephen Suhart, and Diana Dugan. Mention an upcoming event. On August 11th, we are going to be having another one of our sci-fi flick events where we're going to be screening Gattaca. And we'll have some people in conversation about Gattaca. Larry Goldstein, the director of the Sanford Center for Regenerative Medicine, is one of them. And so check up on our website and Facebook pages for further information. So let me introduce the speakers that we're going to have tonight. I'll introduce them all at once, and then they'll each come up. After they'll each give about a 15 to 20-minute talk, and then we'll have a panel discussion with them afterwards. And so remember your questions for them for when we get into the panel part of the discussion. So we have with us Dr. Andrew Friedman, who's a National Science Foundation postdoctoral fellow at MIT and a visiting research scientist at the MIT Center for Theoretical Physics. Before coming to MIT, he did a PhD in astronomy and astrophysics at Harvard in the Department of Astronomy, and received a BA in astrophysics from UC Berkeley. And his background is mainly in observational cosmology, including infrared observations of supernova, which can be used to measure the expansion history of the universe, as well as cosmic acceleration and dark energy. He's currently working on several theoretical cosmology projects, including devising fun experiments that leverage cosmology to help test fundamental physics. He's interested in the intersection between observational astronomy, cosmology, philosophy of science, and the philosophy of cosmology. So Andrew will start, and then we'll hear from Professor Brian Keating, who's an astrophysicist here in the UCSD Department of Physics. He and his team of 21 students and postdocs develop instrumentation to study the early universe at radio, microwave, and infrared wavelengths. He's authored over 100 scientific publications and holds a patent. He received his BS from Case Western Reserve University and his PhD from Brown. He did postdoctoral research at Stanford and an NSF postdoctoral fellow at Caltech before coming to UCSD in 2004. He's received the 2007 Presidential Early Career Award for Scientists and Engineers at the White House from President Bush. And for a telescope he developed at the South Pole Research Station called BICEP. He co-leads a collaboration operating the Polar Bear Research Telescope in the Atacama Desert of Chile. And he's a trustee of the National Museum of Mathematics, a member of the Clark Center Advisory Board, a member of the Math for America Board, and the San Diego Air and Space Museum. And then we'll hear from David Brin, who's a writer-in-residence for the Clark Center, and then is also a scientist and best-selling author, but he's mostly known for his Clark Center writer-in-residence, I'm sure. And his future-oriented novels include The Postman and Earth. His uplift-based Hugo Award winners include Startide Rising and The Uplift War. The Postman, you might remember, is turned into a major film in 1998 by Kevin Costner and is sure to be the subject of an upcoming Clark Center sci-fi flick night. Brin is also known as a leading commentator on modern technological and, I would say, sociocultural trends. His nonfiction book, The Transparent Society, won the Freedom of Speech Award for the American Library Association, and his newest novel, Existence, explores the ultimate question. Billions of planets may be ripe for life, even intelligence, so where is everybody? So we'll hear from each of these in order, and then Professor Keating will moderate and participate in a panel discussion amongst them. So, Dr. Friedman? Oh. I'm sorry. I missed my best slide. If you could just give me a quote, to leave us with a quote from Borges to start.
All right, thank you so much. It's fantastic to be here today to talk about the multiverse, which is definitely one of the most exciting and controversial ideas in all of science. And some of these ideas may definitely sound like they're straight out of science fiction, but believe it or not, the idea of other universes is not only not completely crazy, it's actually a logical extrapolation of our best understood theories of physics and cosmology. That doesn't mean we know for sure that other universes exist, but it does mean we know enough that we have to take these ideas seriously. And so I'll be joined tonight by Brian Keating and David Brin, as discussed. And hopefully we can paint an interdisciplinary picture behind the multiverse. So I'll start by giving an overview of some of the theory behind the different levels of the multiverse that people are talking about today. Brian will follow up by talking about some of the leading experimental evidence we have that makes us take this picture seriously. And David will conclude by talking about how human beings might fit into this picture. And to be fair, the entire topic of the multiverse could take up an entire university-level course. So we're just going to give you kind of a taste, very, very much the tip of the iceberg, about what we can cover in about an hour. And I'll draw heavily upon the ideas of my MIT colleagues, Alan Guth and Max Tegmark. And they couldn't be here today, but they have a good excuse. They're currently trapped in another universe, about 3,000 miles east of here, also known as the Multiverse Institute of Technology. And I say this in part because we recently had a chance to, all three of us, give a talk at the same panel at the American Astronomical Society Conference in Boston on a special panel entitled Multiverse, Observation and Theory. And here we are at the biggest astronomy conference in the world talking about parallel universes. So what this tells you is that these ideas are becoming more and more part of the mainstream. People are regularly publishing articles in the top physics and philosophy journals on this stuff. So while some people still hate the idea of the multiverse, and there are many, many skeptics, this is by no means universally accepted in the scientific community, fewer and fewer people are dismissing it just because they say it's crazy. So it's great to be here at the Clark Center, and I actually only heard about this place through David Brin and Brian a few months ago. And it's kind of amazing that a center devoted to the human imagination actually exists. This seems like the kind of a place that would only exist inside of a science fiction novel. So, being here kind of makes me feel like I'm somehow turned into one of David's characters. But in any case, if these gentlemen were still with us, I think they'd get a real kick out of these ideas, which are all about exploring the limits of the possible. So the question at stake is, in some sense, the biggest question of all: how big is the world? How far does reality extend? And it's interesting that to human beings living just a few centuries ago, the Earth itself might as well have been infinite. And today we've kind of come full circle because the leading theory of modern cosmology is very much consistent with us living in a very large space which could be infinite, of which we can only access a finite part. And reality could be even bigger than that. So one arc of the multiverse story is the so-called Copernican principle, the idea that human beings don't occupy a special preferred location in the universe. Each time we think we've reached some limit where we're right at the center, we find that we're kicked out of that preferred perch. So we now know that the Earth is not at the center of the solar system is not the center of the galaxy. Our galaxy, the Milky Way, is just one of hundreds of billions that we can observe in the part of the universe we can see. And other universes are just sort of the latest chapter in this story. But the Copernican principle can definitely be taken too far. I happen to believe that human beings are very, very important in the cosmic scheme, and life itself is very important. You know, aliens aside, we're the only beings that we know of that can talk about things like the multiverse and think about how we might fit into it. So as a rough outline, I'll discuss some of the various levels of the multiverse that people are talking about today, and I'll very much follow the scheme developed by Max Tegmark at MIT, because I think it's one of the most clear ways of putting forth the ideas. Although this list is by no means exhaustive. Brian Greene, in his book, talks about 9 different levels. I'm only going to really talk about 4. And when Brian and David and I were discussing this, we brainstormed and came up with about 20 or 30 different ideas. So this is just the tip of the iceberg. So I'll discuss the first level, which is basically parts beyond what we can see, beyond our so-called cosmological horizons, and maybe universes perhaps living inside of black holes. I'll talk about different universes produced by the theory of cosmic inflation, and Brian will talk about some of the best evidence we have for this. I'll talk about the many worlds of quantum mechanics, and even universes with other laws of physics. And David will hint at just a few of these in his talk. But since the evidence for at least the first level is very, very, very strong indirect evidence, it's not a question so much about does the multiverse exist, it's a question of how many levels are there. And these do get more and more speculative as you go down the chain, but believe me, there are even crazier ideas out there than these. So we have very, very strong evidence that the part of the universe that we live in is about 13.8 billion years old. Here is a little baby picture of the universe. This is the so-called cosmic microwave background radiation, the afterglow of the Big Bang, which is like a snapshot of the universe about 380,000 years after the Big Bang. Here's an image of some of the most distant galaxies we've ever observed, and every single splotch of light in this picture is a galaxy. But because light travels at a finite speed, we're not seeing objects as they are now, but as they were when light left billions of years ago. So in this sense, a telescope is basically a time machine. So when you combine the finite speed of light with the finite age of the universe, there's a limit to how far light can travel since the Big Bang. And you might think that limit is exactly 13.8 billion light years, but in fact, it happens to be a little bit farther than that because you have to take into account the fact that the universe has been expanding all along. So we actually think the universe is not only expanding today, but actually accelerating and speeding up in its expansion due to so-called dark energy, this unknown cosmological anti-gravitational force making galaxies move farther and farther apart from each other. And so it turns out that the distance light can travel since the Big Bang, if light was emitted right after the Big Bang and is just arriving at us today, those objects now are about 46 billion light years away. So if you're willing to take seriously the idea that perhaps maybe 100 billion light years in that direction, there's a galaxy, then you're already talking about the first level of the multiverse, parts beyond what we can see. And this picture is actually very much the standard view of modern cosmology. And ultimately, it would be crazy if space just sort of stopped right there, if there was an edge to space. But there are relevant boundaries. One thing that's interesting about the cosmic acceleration is that the expansion of space itself can actually outrace light. This is actually allowed in relativity. And what this means is that there are places that are so far away that you'd be kind of traveling upstream. And if you tried to reach them, you could never reach them, even if you traveled at the speed of light forever. And this is, I think, why, even though these other parts are really part of the same larger space, it's why they really deserve to be called separate universes, because they're causally inaccessible in principle, at least as far as we understand things. So just a little bit about cosmic inflation. It's our leading theory of the early universe cosmology, developed by Alan Guth at MIT and others. And the idea essentially is that there was an exponential period of expansion of space in the first instance of cosmic history. And what this does is it solves a number of cosmological problems which would otherwise be ridiculous mysteries. Brian will talk about this a little bit. It makes a number of very, very risky testable predictions about things we can observe, let's say things in the microwave background radiation. But in addition, it predicts that space is much, much larger than the part that we can see. Because if enough inflation occurred to solve these problems, then it's guaranteed, essentially, that the universe extends beyond the part that we can access. So any evidence for inflation is really, really good indirect evidence for at least this first level of the multiverse. So what do these other universes look like? The idea is that they would have the same laws of physics as our universe, but they would have different constants of nature, different things like values. But the same constants of nature, the same values for things like the speed of light, the amount of dark energy, the mass ratio of the proton and electron. But what they would have is different initial conditions, as illustrated by these slightly different baby pictures of the universe, and therefore different outcomes. So the distribution of galaxies would be different slightly in each of these universes, and maybe one of them is a place where a planet like the Earth formed, and another is a place where it didn't. So there may be other kinds of universes that are beyond what we can see that are practically right next door in our galaxy. You've all probably heard of black holes, these regions of space and time that are so gravitationally distorted that if you fell in past the so-called event horizon, you could never escape. And we have very, very strong evidence that black holes exist at the center of essentially every galaxy we've observed. Very, very large black holes, billions of times the mass of our sun. We have very strong evidence that smaller black holes the size of stars exist. There's probably a black hole within 100 light years of our position right now. But what we don't know is what happens inside of black holes. We don't know about black hole interiors. Our current theories of physics are not complete enough to describe that. So we don't know, for example, if you would be destroyed by a so-called firewall of high-energy radiation as you pass through the event horizon. Maybe you'd be spaghettified and stretched into an infinitely thin strand and obliterated by the differential gravity of the tidal forces for a small black hole. But for a large black hole where the tides would actually be less, maybe you'd survive. Maybe you would actually find yourself in some other part of space-time. So for example, we don't know if some or all of black holes are actually so-called wormholes, these connections between distant parts of space and time. And so maybe, if that's possible, if you fell into a black hole and you might end up somewhere else, you might ask, maybe we're already inside of a black hole. So this is actually not as crazy as it sounds. People are actually really seriously considering, from a theoretical perspective, the idea that an accelerating, expanding universe as seen from the inside might be sort of dually described by a black hole as seen from the outside. And some people take this idea really, really seriously, including Lee Smolin with his theory of cosmological natural selection. He envisions a network of universes within universes produced by black holes, and the essential idea here is that the universes that would sort of do best in this scenario are the ones that have the parameters of nature that would allow them to produce the most black holes, produce the most progeny. So this is kind of a Darwinian view of this picture. And the most speculative claim of this idea is that the same parameters that actually lead to most black holes being produced are also the same ones that are required for life to exist. So although this particular theory, I think, has some problems and may be wrong in some of the details, it's a very, very interesting speculative suggestion about how you might think about Darwinian processes on cosmological scales. So coming back to inflation, after it stopped in our universe, the expansion proceeded according to kind of a more leisurely pace. Even the cosmic acceleration that we're experiencing now is very, very small compared to what happened during inflation, we think. But it turns out that just because inflation stopped in our part of the universe, it's actually very hard to build models where inflation only happens once. It's the kind of a situation where if inflation stops, let's say in a little bubble right here, it's probably going on somewhere else. This is the idea of so-called eternal inflation. And as you might guess, these universes, these are different in character than what we've talked about so far. These form the sort of ingredients of the second level of the multiverse. But these places are also so far away that we couldn't reach them even if we traveled at the speed of light forever. So they're separated from us causally in the same way that even the first level ones are. So some other theoretical ideas that lead us to take this picture seriously come from string theory, which is our current best candidate for a theory of so-called quantum gravity, which would combine our understanding of quantum mechanics, our theory of the subatomic world, with general relativity, which describes our theory of gravity on the largest of scales, including cosmology. And in order for string theory to work, you actually need extra spatial dimensions. So we're all pretty familiar with the standard, 3 spatial dimensions and 1 time dimension. You all successfully made it to this room at this particular time, so you're good with those 4 dimensions. So what would the other 6 or 7 look like? The idea is that, why don't we see them? One idea is that they're actually very small and very curled up, very tiny. If you could zoom into space-time, you would see them. These are sort of illustrations, 2-dimensional projections of what could be these larger, more complicated 6-dimensional spaces. Here's a fun little movie of a cross-section of these kinds of objects. But the idea is that each of these different ways of making a shape like this is a different way that a universe can be. And it turns out that, as far as we know it now, there are literally astronomical number of different possible ways of making these extra dimensions curl up. And so this describes the so-called landscape of possible universes according to string theory. And the connection to eternal inflation with the bubble universes is that eternal inflation would be the physical mechanism that populates the landscape of possible universes in eternal inflation. So for the second level of the multiverse, the idea is that you'd have the same laws of physics, but in this case, this is the case where we actually think you'd have different values of the dimensionless parameters of nature, things like the mass ratio of the proton-electron, things like the amount of dark energy. And so the idea is that any evidence we have, like from the CMB for inflation, is indirect evidence for this level as well, because it's actually really hard, if inflation happened once, for it to only happen once. And this also explains another mystery. This is the mystery of the so-called fine-tuning for life. So it turns out that, to the best of our understanding, if you look at these parameters of nature and you change them just a tiny amount, it actually makes it very, very difficult for life to exist as we know it. So for example, if you increase the amount of dark energy, the universe expands and accelerates so fast that galaxies never form. So if you think galaxies are a necessary prerequisite for life like us, that's bad news. If it turns out that if you tweak other knobs, you can make it so no stars ever form or no planets ever form. You can even make it so that there's no periodic table, there's no chemistry, no stable elements. So these are all kind of pretty crucial prerequisites for life as we know it. And this leads to the mystery. Well, how is it that we have the right values that allow for our existence? So were we just lucky? Were those values perhaps chosen by some force or some intelligence? Or perhaps, if the multiverse exists, if there are many universes with different values of these parameters, it makes it more plausible, maybe even inevitable, that at least one would be just right. This leads us into the very controversial anthropic principle. Essentially, this idea states that the physical constants must be such to allow our existence. If there's only one universe, this is clearly a tautology. This just says we exist because we exist. But if there are many universes with different values of the constants of nature, then this argument has logical, explanatory, and predictive power. So for example, let's say you consider something like the value of the distance between the Earth and the Sun. You could ask the question, why is it that this distance is exactly right to allow for water to be liquid on the surface? Isn't this amazing? This is incredible mystery. But we're actually not that surprised by this, especially because we now know that there are literally thousands of other planets that we've discovered, probably billions of other planets even in our own galaxy, and they have a distribution of distances between the stars and planets. So there's an ensemble. And of course we have to find ourselves living in a place that's consistent with life like us. It's a very similar argument is, well, why don't we find ourselves living in empty space? Because most of space is empty. Well, that just doesn't work for human beings. And crucially, the logic is exactly the same for the multiverse. So switching gears to a different level of the multiverse from quantum mechanics, level 3, this is the view that's percolated most into popular culture, the idea of parallel timelines, the idea of what if I had made a different choice? How would my life have turned out? This is the idea that the observer or the universe splits with every quantum event. This is illustrated by this fun little film reel. and you might recognize Schrodinger's cat here. This is the idea that reality sort of takes on a branching structure. And this might seem like it has nothing to do with the other levels we've discussed so far, but in fact, some new ideas, very speculative ideas, suggest that maybe this level is actually unifiable with the first two levels within a cosmological context. So it's possible that the many worlds of quantum mechanics are actually really out there, someplace far away in space. But it's also possible that they might actually be, in a sense, right on top of us. We don't know very much about this question. This is why it's a really interesting place to be working. So what evidence do we have for the many worlds view of quantum mechanics? Well, some people think that the many worlds view provides the best explanation for what's actually going on in experiments like the famous double slit experiment. If you have beams of photons sent through a screen that has two slits, it'll form this standard quantum interference pattern, this wave interference pattern. But the amazing thing is that if you do this experiment and you send single photons through one at a time, the interference pattern still builds up. So this leads to the question, what was it that the photons were interfering with? Well, they're behaving exactly as if they're interfering with other photons. Maybe we should take seriously the existence of these other photons, which essentially would be photons in other universes as described by quantum mechanics. Another idea comes from the idea of quantum computers. These are computers that could perform calculations incredibly faster than equivalent classical computers. If these are built and they perform these calculations, then the question becomes, where were the computations performed? It seems very difficult. This is not an airtight argument, but it seems difficult to understand where the computational resources are. So one idea is that perhaps you could think about this as the computation being shared amongst many universes. The problem with this picture is that there are literally dozens and dozens of interpretations of quantum mechanics, more than even ideas of different kinds of levels of the multiverse that I've seen. And the other interpretations at this stage essentially give the same predictions as the many worlds view. So we need a tiebreaker. We need a new theory, perhaps quantum gravity, that will allow us to modify these interpretations so they actually make different experimental predictions and are therefore distinguishable. But I will say that the many worlds view is still consistent with everything we know about quantum mechanics. So far we've only talked about levels with the same laws of physics. The most speculative level is the idea that maybe universes with different laws of physics might be okay. These would be described by other kinds of mathematical structures, as illustrated by these fun geometrical shapes here. Why would you take this seriously? There's this interesting question about why math works so well to describe the physical world. Eugene Wigner, a Nobel laureate, called this the unreasonable effectiveness of mathematics in the physical sciences. So one answer to why math seems to work so well is that maybe the world at its core is fundamentally mathematical. Maybe there is a mechanism, which we don't quite understand yet, by which mathematical existence actually gives rise to physical existence. This is clearly the most speculative level we've discussed so far, but trust me, there are much, much crazier ideas out there. So is this science or not? So it's not an understatement to say that these ideas represent kind of a battle for the soul of science, at least in this corner of theoretical physics. Skeptics of these theories think that if you go down this rabbit hole, it's the end of science as we know it. How can you ever make any testable predictions when it comes to regions which seem inaccessible in principle forever? So rather than taking that attitude and kind of giving up, I actually view this as a challenge and an opportunity to think of new and clever ways to try to test these kinds of ideas. It's really important to remember that parallel universes themselves are not a theory. They're predictions of specific theories like inflation, like string theory. And in order to test a theory, we don't need to test all of its predictions, only some of them. But you have to take the theory as a coherent whole. You can't just pick and choose which of its predictions you take seriously. You have to take them all seriously until a better theory comes along. Maybe there'll be some other better theories that come along that don't have a multiverse as the predictions, but that's not the current state that we're in. So in summary, some people still hate the multiverse, but I think a lot of this has to do with just purely aesthetic judgments. I admit that I find these ideas fun, cool, and interesting, and I think, okay, what has to be true about the world beyond what we know in order for these ideas to be testable? And I don't say that I believe in the multiverse with 100% certainty, but I think that as long as we are trying to move forward towards testing these ideas, then we're still doing science. And quantum gravity has some pretty interesting suggestions. One idea is that space and time might not be fundamental quantities, but might actually be derived from more primitive concepts, such as how quantum mechanically entangled and connected two regions are. So it may be that some places which naively look really, really far away, according to general relativity, might in some sense actually be very, very close to us. So as soon as you consider things like wormholes, for example, you're considering ideas that would allow what seem like inaccessible regions to be accessible. So overall, the first level of the multiverse is pretty solid and uncontroversial. It's just the idea that the part of the universe we can see is not everything. This is the standard view of modern cosmology. If you accept the logical extrapolations of our best physical theories, inflation, string theory, quantum mechanics, general relativity, you'll take seriously level 2. If you think that quantum theory makes the most sense in the many worlds perspective, you'll take seriously that level. And if you think that mathematics is fundamentally discovered and not invented, then you'd be willing to take seriously this level. And who knows how many more levels there are. In any case, this is a really, really fun thing to think about. It lies kind of right at the sweet spot between philosophy of science and theoretical physics. And it's certainly a fun and exciting time to be a scientist, at least in this universe. Thank you very much. So next we'll hear from Brian Keating talking about some of the experimental evidence for inflation. And we'll follow that up by hearing from David about putting this all into a human perspective. Thank you.
Okay. Can you guys hear me? Okay. Okay, so I am the token experimentalist on the panel tonight. So I brought with me my own baby universe. I hold in my hand an actual universe. And in this universe, Sheldon's not wearing a shirt at all. It's the most popular one of all. Okay, so Andy gave an excellent introduction to these deep and mystical theories that seem to be both in vogue and quite speculative, but at the same time may have tremendous impact, just as the Big Bang Theory was a pejorative. The name itself is a pejorative, but is now accepted by all but a few people in certain parts of the country as being exact description of nature. So now maybe it's not so crazy to think perhaps we do live in a multiverse. So I want to talk about this. Andy showed this slide. This is a famous woodcut from the 1500s when they just had invented Photoshop. And what it depicts is this ancient quest. Cosmology is a very easy science to do in one sense because you can do it with just your eyes and your brain. And in fact, that's how early humans did it. That's the oldest science. People looked up and wondered. And this depicts this character looking back in space, and as Andy said, your eyes, just like a telescope, are time machines. So you can look back in space, you're looking back in time. So things that are far away from us. This artist who conceived of this woodcut was conjecturing what they might look like. Now this looks not too dissimilar from some of the Escher paintings and woodcuts that we saw at the end of Andy's talk. So how crazy is it really to speculate about such things? And it's really, as I said, one of the oldest quests of humanity. Here's a more modern depiction of it that I've stolen. And this depicts sort of a very crude space-time diagram that shows things today down here, and then in the past, this beach ball flattened out and laid flat as if you're God looking down on this region of the multiverse. And the preceding epoch to when these most ancient photons left the primordial plasma, that epoch, we believe, is called inflation. And I'll talk about that because the hypothesis is that if inflation occurred, as Andy mentioned, in many models of inflation, it still is continuing, it still exists, and it has so-called eternal inflation. You cannot shut it off. In that case, there may be an infinity of universes, and in fact, this diagram may be wrong. There may be no dawn of time, and we may be back to the old Aristotelian and pre-Aristotelian notion that the universe is infinitely old, and that baby universes perhaps spawn cyclically into and out of existence. I'll spend a lot of time focusing on discoveries that we made using this image and images like it with our telescope at the South Pole called BICEP, and how we infer from the properties that we see here what this epoch might have been like. And then the logical extrapolation that you must make is that if this occurred, if this inflationary epoch occurred, then perhaps something like the multiverse must also be mandated in some theories of physics, both from a coupling of the inflationary high-energy physics of the early universe and also things like string theory, as Andy mentioned. This has attracted a lot of attention from worldwide organizations. This is on the front page, our discovery with BICEP 2, the so-called space ripples of the Big Bang smoking gun. So I always like this headline down here from The Economist. Sounds like some guy just suddenly sees the start of the universe. Wow. If you're looking in one, oh, I saw it. It's like a meteor. And then, of course, the best newspaper in all of science is, of course, the UCSD Guardian, which is a little bit more circumspect and very calm in their notion. They said, UCSD scientists prove inflation theory. Well, that's pretty awesome. I don't think you can even prove a theory in physics, let alone the fact that we did it all by ourselves, which we didn't. So I'm going to talk to you about this, and I always say it's a mystery. It's a mysterious universe in which we live. There's a mysterious galaxy not too far from here where you can buy David's books. But there's also a mysterious multiverse. And so I don't want you to ever come away, especially I see a lot of young people in the audience, and that's wonderful. I want you to come away with the notion that there's way more to do than has been done. And the people that are up here really haven't even scratched the surface. And it's your job to come up not just with the theories and the conjectures, but actually follow through with it. Learn the math, learn the science, learn the physics, build the experiments, travel to these distant places. That's what I want to inspire you guys to do. And even we have some older people that could be inspired to do that too. So I always say it's a mystery, and the mystery, like all great mysteries, you can maybe phrase it in the form of a murder mystery. And I'm going to lay out a few different of these bullets, and I'm going to hopefully motivate the fact that there is evidence that inflation occurred. And then following on from Andy's talk, that perhaps if inflation occurred there too, therefore also did the multiverse. The multiverse somehow follows from this explanation. But I'm going to leave in a little wrinkle at the end, so I want you guys to stay tuned. I'll wake you up for the end. So I'll talk about the scene of the crime where we go and what the very early universe was like. I'll talk about our crime lab where we built a forensic tool to appraise what the early universe must have been like. And then the so-called smoking gun, as the New York Times front page decried, that we seem to believe is indicative of this inflationary, explosive expansion of space-time. And then perhaps the jury's still out. There's still some controversy about our results and even some very interesting conjectures for the future. So just a very quick diagram. This is probably the most technical diagram I'll show. This is a slide that our collaboration put just to demonstrate the major features of cosmology in one slide. It's very difficult to do, but nevertheless, it starts with a Big Bang. At least our portion of the multiverse, or in the region that when I was a kid, there was only a universe, okay? So I have to get used to it, just like when I was a kid, there were 9 planets. But then people like Adam Burgasser and others came along and killed off Pluto. And so now I have to always correct myself that there's only 8. So we talk about the Big Bang as being the local origin of, as Andy said, this observable universe that we can detect that's roughly 40 plus billion light years across. That instant is called the Big Bang. Time equals 0. So you set your watch, and then roughly a trillionth of a trillionth of a trillionth of a second after that came this violent expansion of space-time called inflation. And then after that, things and events are listed here that are a little bit more prosaic in terms of their impact, but they're all observable relics. They all produce relics that we can see today, even if they're not in the form of light. We can detect the processes, the fact that we observe elements today, light elements like helium and hydrogen. Those are relics left over from the Big Bang. Very little hydrogen can be formed outside of laboratories. So what we see is residual primordial evidences. This is trace forensics from the Big Bang itself. When the protons combine with electrons that were around since the very beginning, then the cosmic microwave background, or CMB, is formed. And this is this famous 3 Kelvin background. It's depicted here on a globe of the sky flattened onto this beach ball. And this depicts what you'd see with your eyes if your eyes were sensitive to microwaves and you looked out at the night sky. You wouldn't see constellations, you wouldn't see stars, planets, or galaxies. Instead, you'd see fluctuations in the microwave background's temperature, its intensity, and its polarization. And that's this epoch here. And so what we're trying to do is use this image that we've made and other groups have made of the very early universe, 380,000 years after the Big Bang. Take this image and use it as a type of film. Okay, so it's a little bit strange to think about light being a film, and nevertheless we have to think about it in that way. We're attempting to expose waves of gravity on these photons. Okay, so probably half the audience doesn't remember film, but half the audience does. So a film was this ancient thing that we used to use 10 years ago to take pictures, and it would expose light. Here we're not exposing light, we're exposing gravity, waves of gravity, gravitational radiation from the inflationary epoch on this background. So it's as if we're looking at this beach ball, and what we're trying to see are not the temperature fluctuations themselves, but distortions and ripples. This thing is wiggling like a ball of jello. And those wiggles are imprinted by waves of gravity. Those waves of gravity are produced during the epoch we call inflation. We built a telescope to do that. And in doing so, we were guided by the fact that we've confirmed many of the predictions of inflation. Andy mentioned a few. I'm not going to go over them. But inflation is one of the most well-tested, if not proven theories, despite the UCSD's Guardian headline. It cannot, in some sense, be proven, but even to the extent that we can understand ways to falsify it, it's been passed with flying colors. So we can't say that we've proven it unless we can rule out every one of an infinity of possible alternatives. But in this case, we have so much credulity in the model that it behooved us and myself to invent this experiment to go after this unique signature of inflation called gravitational waves that produce so-called B-mode polarization. So we're looking at this pattern of microwaves. They have polarization properties associated with them, just like polarized light reflects off the ocean surface. You can use polarized sunglasses to see it. And we're looking back at this pattern to see waves of gravity exposed from the very earliest instances after the Big Bang. So what is the CMB? I want to show you this, just a kind of cartoonish glimpse. So if you go out into low Earth orbit, and you looked and your eyes were sensitive to microwaves, this is what you'd see, an amazing depiction. The beauty, the grand elegance, if you're a religious person. This is the face of God. It's so beautiful. No, this is what you'd see to first approximation. You'd see nothing. It would be this uniform, boring, puke orange glow that your eyes would detect no discernible pattern from. This is the so-called 3-degree Kelvin microwave background signal. This is the primary tool that precision cosmology has been used to extract the parameters of the very early universe. Now, if you take away the average level that you see in each direction on the sky, you're left with these fluctuations like on this beach ball. And this is quite an exhilarating map to see. An image like this was called by Stephen Hawking like looking at the face of God. Ironic because he's a devout atheist. But nevertheless, looking at these images, looking at these patterns, we've refined our understanding of the global properties of the universe, its age, its mass, its energy, its possible future evolution. It's just incredible to think of everything we've accomplished just with this, and now we've endowed it with another observable called its polarization, which I'll talk about briefly. So it was discovered in 1965. So I always say it's the last great discovery in astronomy from northern New Jersey. I'm a New Yorker, so I'm entitled to make fun of New Jersey. And it was discovered actually serendipitously back when this was the entire internet. So Steve and Sue and Cindy are here from Viasat. So this used to be the entire internet. It was one satellite that communicated around the entire Earth. You bounced signals off of, even more slowly than you could do with an old 300 baud modem. And you'd be able to communicate with it. But when they launched it, they found they couldn't get rid of this glow in the background that seemed to come from all directions. And that, of course, turned out to be this 3 Kelvin or 2.7 Kelvin microwave background radiation. So that was its discovery. They won the Nobel Prize for this in 1978. And in the old days, I usually say to people, if you tune your television to a UHF station there's no signal, local signal, you would get static on it. But nowadays, no kids know what static is, okay? YouTube never gets static. But about 1% of the static on an old-fashioned CRT-type monitor would be from the Big Bang itself. So the orange glow that you saw originally was the background radiation. It's 3 Kelvin. Then there are tiny little fluctuations predicted by our late colleague Art Wolf, who was at UCSD, predicted that there should be fluctuations in the microwave background only 2 years after its discovery. Quite astounding prediction, and that was borne out in 1992 when the COBE satellite measured these imprints, these fluctuations in the microwave background for the first time. And that was later awarded the Nobel Prize in 2006 to George Smoot and John Mather. And those fluctuations led us to believe that there must be some force responsible for the fluctuations on the largest scales in the universe. Just to give you an example of how small, I say that these are large. So the microwave background itself is 3 degrees Kelvin. Subtract away 3 degrees Kelvin, you're left with fluctuations that are about 1 part in 100,000. How big is a part in 100,000? Well, the surface of a bowling ball, if you map the surface of a bowling ball and compared it to its average radius, the fluctuations are about a part in 10 to the 4th, or a part in 10,000, meaning that the surface of a bowling ball, which most people consider pretty smooth, is actually much, much rougher than the surface of the last scattering surface than this image would be if it were depicted as a bowling ball. Again, not my bowling ball, because I'm a terrible bowler, it has a lot of dents in it. So the question is, where do these fluctuations come from? And the inflationary model has posited that these fluctuations come from quantum behavior in the early universe, in the fabric of space-time itself. So what are we trying to do? We're trying to take this image. This is now just a purple and blue. This is the actual COBE image of the full sky, laid out flat again. And we're trying to understand from this image that we see that dates to 10 trillion seconds. Sounds like a lot. It's 380,000 years after the Big Bang. We're trying to infer from that, what did the universe look like a trillionth of a trillionth of a trillionth of a second after the Big Bang? 50 orders of magnitude extrapolation from the physics of 380,000 years after the Big Bang to essentially right at the beginning of time. So what would that be like doing in more human terms, in a more human scale? So imagine you look at this creature over here. You biologists here will recognize this, and if you do recognize it, please come to Gattaca event on August 11th. This is what you look like 1,000 seconds after you were conceived. Okay, this is called a blastocyst. It's roughly 100 to 1,000 cells assembled into this nice little soccer ball package. And if you were trying to extrapolate what this image looked like by looking at, say, this handsome devil here, if you were looking at him and you were trying to extrapolate from this image, how could you possibly expect to do that? Okay, so here's David, our lovely co-collaborator tonight. So here he is at 2 billion seconds old. I think that's roughly correct. You guys can figure out how old that makes him in more human terms. Now imagine trying to do this, looking at a picture of him and inferring what his blastocyst looked like. I think he looks like his mother there. But this is only a factor of 2 million extrapolation. This is 50 orders of magnitude, 46 orders of magnitude more. And yet we think that we can do such a thing. And that has to do with the simplicity, although it's complicated, the simplicity, the elementary nature of space-time at very, very early epochs when the universe produced the CMB radiation that we see. So how do you do that? Well, it starts with a pairing of theorists and experimentalists thinking about ways that you could observe directly the signature of inflation. So what inflation predicts is that there's a background, just like there's a background of light, there's a background of gravitational waves. They come through space-time and they shake it and shudder it, and it causes tremors and reverberations. Those induce a specific kind of swirling motion in the polarization patterns that we see in the Big Bang. That's called B-mode polarization. For cognoscente, it's an analogy to the magnetic field, which is written as a certain vector operation. So we attempt to measure these little polarization orientations and their intensity on the entire sky, or at least on this patch of sky that we can observe. And the smoking gun has been called many times to observe this pattern. This is a simulation, and I'll show you later some real data, and you can compare for yourself. So how do we do that? We built an experiment called BICEP 1, and then we built a successor called BICEP 2, including the very hard work of my graduate student, John Kaufman, who's in the audience, who just became Dr. John Kaufman. This is a telescope which is not only one of the world's most powerful telescopes, it's also the world's most southern telescope and the coldest telescope in the known universe, and I'll explain why that is in just a bit. Here it is. If you ever see this picture, you're in really bad shape because this is sunset at the South Pole, which happens once per year in March, towards the end of March when spring starts for us. That's when fall starts at the South Pole. So you won't be getting out anytime soon if you see this beautiful sunset. It's a relatively large collaboration, although not compared to, say, a particle accelerator. About 12 or 15 different institutions. And we built this experiment. We started with BICEP 1 in 2005, and we upgraded to BICEP 2, and we have many more upgrades still to come. This is what the telescope looks like before it was shipped down to the South Pole. It's a refracting telescope. It's actually not that big. This length here is about 5 feet long. But the unique thing about this telescope is that we designed it to be cooled down almost to the temperature, in fact, to the temperature of the cosmic background radiation itself. So it sits at 3 degrees Kelvin. The warmest parts of it are at 3 degrees Kelvin. It sits on an ordinary telescope mount. It can scan back and forth, look up and down. It's quite simple. If you did a cross-section through it, you'd see, at least in the original design, it stands for background imaging of cosmic extragalactic polarization. Light comes in. It's a refracting telescope like Galileo used to first change mankind's conception of what the universe was like 405 years ago with the training of his small refracting telescope on Jupiter and on the moon. So light comes in, gets focused on detector. The detector arrays sit at a quarter of a degree above absolute zero. So these are cooled down to 453 degrees Fahrenheit. Sounds really cold. And in fact, it is. People wonder what the lenses are made out of. It's very simple. We use a very high purity version of what we used to have in these old milk jugs. I don't know if I've never seen one in California. Maybe they're banned. But it's just high density polyethylene. It makes a good lens. It's transparent from microwaves and induces almost negligible polarization contamination. So now where would you put such a telescope? Well, here's the Palomar Observatory. So if you converted before 2 billion seconds into years, you can calculate what year David was born. And I'll just tell you that he was born, so they built this telescope for David. This was built the year before he was born so that he could use it to think about the universe as he's done throughout his career. This telescope, though, was built and put in north of Julian, and it was done so for a reason, because in 1949, that part of San Diego was quite dark. And its background, what it's looking for is light. So you had to put it somewhere dark. We wanted to put our telescope somewhere cold because we're looking for something that is analogous to heat. So we want to take it somewhere cold. So we took it to Antarctica. And if you go out into space, you can look at Antarctica like this. And the center of the Earth's axis, the southern point on the Earth's axis of rotation, is the South Pole. And it's a continent. Antarctica is an actual continent. I actually brought some pieces of it home with me the second time I was there. But don't tell the governor. No, there is no governor there. It's a lawless continent. There's only about 1,200 people there at any given time in the summer. And right now in the winter, there's about 200 people. So the entire continent is popular with 200 people. So you can actually get to a lot of superlatives, I was thinking when I was down there. I mean, I've never been like, it's hard to be like the fattest person on the North American continent. But I could actually do it in Antarctica. I could be the fattest. You could be the shortest, the tallest. The oldest, the youngest. See, there's a continent of superlatives, including the fact that it's the highest continent, it's the coldest continent, it's the windiest continent. The South Pole sits at about 9,000 feet above sea level, so it's a little bit of the way into space, where you'd like to be ideally. If you go to this website in the summertime, you'll see a picture that looks like this. Right now it'll be completely dark, but there's a webcam that shows you what the weather conditions are like, and it's usually 100% chance of white. And if you think about it like a snow forecast, this is 9,000 foot deep base, if you think about skiing, okay? But unfortunately, it's all flat, so you can't really get too far. You can go cross-country skiing. We go there despite the fact that there are very known to be very hostile natives that live there. Despite that fact, we still went there. So it's a very dangerous environment, but some of my colleagues are here. They treat me worse than that. Okay, so when you go down there, there's no Walmarts, there's no Targets. You can't buy clothes when you're down there, really, besides souvenir T-shirts to give to your friends. So instead, you have to stock up with all the clothing you're going to use for the next month, 2 months, 9 months, or a year. You pack them into these bags, and you take all these articles of clothing, including these really cool semi-inflated moon boots, we call them, so that you won't get frostbite. If you wear normal sneakers, your feet will freeze due to the conductivity through the rubber. You catch a flight. Hopefully, if you wake up in the morning at 5 in the morning in New Zealand, you don't go outside and see this. But the first time I went down, I did. This is a C-130 cargo plane that flies from Christchurch, New Zealand to the McMurdo Continental Base in the U.S. This is also 1/10 of the New Zealand Air Force. It's pretty interesting. Okay, you sit there. It's a beautiful, very spacious, lots of legroom. No, it's a terrible environment to be on. If you notice, there are very few windows, if any. The pilots have windows, thankfully. But there's only 2 or 3 other windows in the whole plane. There's no bathroom on the plane. You have a little pot called the honey bucket. Don't ask me why they call it that. And you're served, your first-class meal is in a bag of some mystery meat. And you sit knee to knee for, luckily, it's only about 11 hours, okay? So, but you build up a lot of frequent flyer points. And eventually, when we end up getting to the South Pole is quite a beautiful place to be, at least the first day you're there. Then it gets kind of monotonous. Some people love it. John Kaufman, he loves it. I get tired of it. You land, here's the passenger terminal. Okay, this is the Admirals Club, President's Club over here. You pick up your light. Remember what this looks like, because you might see a picture of it later on. Okay, when the early original explorers got there 102 years ago, they skied up from sea level to 10,000 feet almost, over waves of frozen snow called sastrugi, and as I said, up above crevasses and terrible, terrible environment. We make it there in 3 hours from the coast, even in the C-130s. And this is a sort of scale model of what they would have looked like in Photoshop. They weren't so happy, and in fact, Robert Falcon Scott said, "Great God, this is an awful place." And little did he know, he would die 2 months later trying to get back from the South Pole to his fuel and food depots. Nowadays, I say it's an awesome place. So this is the actual axis on which the Earth is turning. Pretty cool. So I can run around the world, and even for somebody slow like me, you can do it pretty quickly. But I say it's an awesome place because nowadays it has a kitchen, a greenhouse, libraries, a sauna, can you believe it? A half-size basketball court, and many, many other amenities. You have to prove to your mother that you made it there, so you take a selfie, and you start walking to work, and there's Bicep. So we built this observatory back in 2005. And here's the outhouse. And this outhouse, if you remember what the passenger terminal looked like, is very, very reminiscent of what the passenger terminal looked like. I'm always hoping they get that right. This is a site that also means they're going to spend the winter there. This means the sun is going down. The sun doesn't go straight down like it does here, roughly at some steep angle. It just grazes the horizon. In fact, you don't know where it's going to go down when you're down there. So it just circles around. You can barely see a tinge of green, not from the laser pointer, but you can actually see the green flash for over several hours when you're down there. This was taken by our winter over the first season, Denis Barkatz. I always tell people, they're like, well, what's it like to be there? And I say, it's great, the pay is awesome, you get $75,000, and all you have to do is work one night. There's the sun going down. Okay, so what happened? What did we actually observe? Well, remember this prediction? This is a simulation. One of the nice things about making a big discovery potentially like this is that you get places like the Washington Post to do your graphic arts. So they did a simulation, this pattern taken of what you'd see if there were gravitational waves. And here, in fact, is real data. This is not a simulation. We can compare the predictions to what a simulation, very detailed simulation, would predict, and it shows exact agreement. So we have a great confidence in it, and moreover, the scientific community has spent many, many months, just 3 months, we've had over 600 different publications. Here's just a smattering of them. As of last night, there's 600 publications that are citing our results, dissecting it. This is what scientists do. They have to check and closely observe and make sure that they can confirm and reproduce your results. Otherwise, it's not scientific. So here are the results. The most gratifying thing was this article in the best science news journal there is, The Onion. It said, top theoretical physicists, R&B singers, meet to debate the meaning of forever. So down here it says, we can observe long-term phenomena like the CMB, primordial B-mode polarization, and the love between India Ari and her man. All of which seem to have existed since the universe's infancy. And I want to make them change it to R and B modes because that's... Okay, so when you go back to this, we think that we've observed this imprint of gravitational waves produced by inflation. So if there was an inflationary epoch, what does that imply? Well, it implies, as Andy said, perhaps there's this infinity of universes called the multiverse. There's not necessarily a proof of it, but if this can be confirmed, it would be very strong motivation that perhaps something like the multiverse isn't too crazy. just finish up with a couple questions that I will want to ask David and Andy later on if you guys don't ask. So what can you say about religion? This quote from Paul Davies is quite evocative. I'll just get cut to the point. He says that the multiverse at a certain level seems to be, at least in the anthropic or finely tuned versions, seems to be reminiscent of religion. Not as a pejorative, but just seems to be philosophically, at least isomorphic in some sense, to a religious theory, or to a religious concept rather, not a theory. So this is a very interesting article that I encourage people to read. Getting back to Galileo, what can we say about the God and the universe? So I just say stay tuned. If he had a big bicep, perhaps he wouldn't have faced the Inquisition like this. And I thank you very much, and see you in November, hopefully. Okay, so David will now present.
Close this one.
And then after David's talk, we'll have a short Q&A period up in the front. So please keep your questions for then. Okay.
Sure, thanks. Well, yeah, so then command return. Yeah. So, yeah, this is a very, very exciting. I tried to ask Sheldon to put the word out through David Kirsch and others to see if we can get some of the members of the artistic community here at UCSD to come, and I'll explain an ulterior motive later. Are any of you part of that community? Well, I'm hoping there's some of you here because we have an ulterior motive for giving this talk, and I'll explain in a bit. Now, I've been giving a lot of talks about SETI, the search for extraterrestrial intelligence. I'm on a lot of the commissions, and this next February, Jill Tarter, who was here for one of our wonderful movie nights, on a panel discussion I shared with her on the movie Contact. She is hosting, we managed to talk the American Association for the Advancement of Science, the AAAS, to hold a special session on SETI and METI this next February in San Jose, where SETI is the search for extraterrestrial intelligence and METI is messaging to extraterrestrial intelligence, something that I, as a science fiction author and as an astronomer, have been in opposition to because it's quiet out there, maybe too quiet. And if they're being quiet, maybe they know something we don't know. In any event, we have been learning so much about the universe just in the last 15 years. 15 years ago, we knew of no planets outside of our solar system. None. Now we know of thousands. Thousands. And you're a member of a civilization that's been doing that. And soon we'll be launching new follow-ups to the Kepler mission that will raise that to the tens of thousands, possibly hundreds of thousands, in which case we're going to get a better statistical notion of what the universe is like and create the conditions for a lot of great new ideas for those of you out here who are the brilliant Clarion kids who are going to be taking over from us old fart whippersnappers in the field of science fiction. Now, in addition, why do we want to care about that? Why do we want to look around there? As Ken Ham, the famous creationist, said, aren't they all damned, aren't all the aliens damned anyway? If you look it up, it's amazing. It was in the news the last day or so. One of the reasons we do that is because of otherness. We're a member of a crazy civilization. Most tribes in human history were scared. Most of the time. They had good reason to be. And when the fear level is high, your horizon of tolerance, who you would include, call a fellow human being, include next to the campfire, allow to speak at your councils, was close in. That's the way we are. Fear levels go down, it doesn't necessarily mean your horizons move out. But if you start with an outward-looking spirit, like we tend to have in our culture, in our civilization, then satiability and low fear levels makes us look outward. And we look outward and outward and outward. And some of the fight over inclusion is part of our politics today, our political wars. But if we don't find aliens, then guess what? We'll make them. We already do it all the time. Have any of you had children? Every generation is invaded by a new wave of barbarians. And you know this. But in addition to that, look at the possibilities. Making artificial intelligence. Many people are confident that we'll reach that point in the next 40, 50 years. Whether it's benign and friendly, like in the movie Her, or vicious and dangerous, like in every other Hollywood film. Because out of laziness, it's just easier to create a dystopia, and then your protagonists can go run around shooting things. Or, you know, the whole question of robots, or as in some of my science fiction stories, the uplifting of creatures that are very close to us in intelligence, helping them to go the last step past the glass ceiling that seems to trap dozens and dozens of other species. The Clark Center ran a wonderful event last May with the Smithsonian back at the Reagan Center in Washington, D.C. in May. And one of my the talk I gave there is about this whole question of otherness and whether or not we're going to expand. Well, our notions, this is just nothing. This is nothing compared to the expansion that's been going on in the notion of the multiverse, the universe. So many things have changed in our concepts of the universe just since the turn of the century. I mentioned that 15 years ago we knew of no planets outside our solar system. Now it's thousands. Well, if you had talked about the inflation and the creation of the universe 15 years ago to almost any physicist, certainly 20 years ago, the notion of inflation was around. The notion of the Big Bang has been around for quite some time. But almost any cosmologist would have gotten angry and left the room at just the things that were being discussed on the screen today. And today, those same cosmologists would happily discuss all these things and claim that they never would have gotten mad. How many of you remember that before 1999, you talked to any cosmologists, the Big Bang is not an explosion, and it's not set in anything. It is an expansion of the creation of what is and the expansion of what is, the metric or the measuring sticks. How many of you remember the blowing up of a balloon as being the metaphor? Where everything's getting farther apart from everything else, but there is no outside. And that's all there is. I think one of the most mind-boggling things to me is the agility of physics, that several of my friends who are physicists almost deny ever having said this, that there's nothing else. This is all, it's all self-contained. And now what do we have? We have the richness of concepts, of a context within which the balloon is taking place. It's not that the balloon description was wrong. That is what's happening. But it may indeed have been an explosion into a pre-existing space. And as mind-boggling as it is to me, all of these thoughts, it's also mind-boggling that we should always remain agile. And so the first of these theories was exploding of the multiverse is we have an explosion into an already existing infinite expanse of three-dimensional space. Absolutely stupid to a cosmologist 20 years ago, but that's now one of the possibilities, that there was a pre-existing infinite space, and these are just bubbles opening up into it. And it didn't have to happen because of inflation causes inflation. It could have been just a variation in Heisenberg's uncertainty principle, that all of a sudden, delta E, the energy, was infinitely available to be borrowed from. Now, there's also the notion that this infinite space is a context within which you have this inflation. And if it is, then it's likely there's other inflationary episodes next to it. And suddenly you have the manufacturing of fresh space, the manufacturing of metric. And this feeds on itself. And I just don't have time to talk about it, and that's my excuse for not talking about it, rather than the fact that even though I have a PhD in physics, these guys are out of my league. I could not parse these equations if my life depended on it. The question of whether or not in some of these bubbles, not only the initial conditions, as Andy spoke of, would be different, but the physical laws would be the same. Therefore, you'd have galaxies, they just wouldn't include us, they'd be different. But also in different bubbles, they might have different physical laws. The staggering fact of our bubble, the most amazing of all the physical laws, was the one finally parsed by Einstein. And of all the brilliant minds of his time, none of them actually thought it out. We're used to thinking that time is the standard against which all things are measured. But time isn't. The standard invariant is the speed of light, and time can vary around it. I've thought about that a lot. I haven't a clue what that means. I can show you equations. Maybe in one of these other universes it makes sense. Now, here is something that is really amazing, and that is, can we measure any of these things? The theological question of whether or not this makes any sense. Well, because if all of these universes are permanently out of reach, then isn't this just tossing things around in the air? Isn't it just science fiction? Because I create universes all the time. So do some of you. But in fact, there are a few possibilities. And one is searching the microwave background radiation for the tiniest images that might be appearing on our bubble if it contacted another bubble. And this you can intuitively see. Bubbles contact bubbles. What do? You get a ring. And so searches are going on right now. One thing we do know is that if there are any such clues, they're extremely small because we haven't found them yet. Well, there are other possibilities. And one is that singularities make universes. Now, this is mind-blowing. And they've actually known about this for quite some time. Hawking and all that, they were talking about this back around 1990, even back in the 1980s. And that is the notion that when you have a very, very large star, it explodes as a supernova, the remnant converges into a black hole, and this folding of the metric in space and the matter that pours into it might result in the creation of a singularity that has, you saw some illustrations in Andy's talk, of a white hole that then creates its own Big Bang. And it does not have to be a Big Bang of the same magnitude of mass as fell into it. Then you just get the mass of a star, or in the case of the center of our galaxy, the mass of, a few 100 million stars. No, you could, in theory, create a whole new universe, and it is detached from ours in ways that are kind of mathematically mind-boggling, but that the brainiacs think are highly plausible. And this new universe takes off. So that every time you form a black hole, you form a new universe. And I'm going to point out here that where's the darn button?
It's on the tape.
It's on the tape. Oh, there it is. Okay. Well, now, this is that threshold that they were talking about. And the photons that you see when you measure the 3-degree background radiation, they are the original photons that escaped when the electrons all over the universe at 380,000 years after the bang, suddenly it was cool enough for the electrons to fall down, become in orbit around hydrogen, around protons, and suddenly the universe became transparent. And these are the original photons from that time. And there are presumably no photons from before that time because they were constantly hitting free electrons. But it's the imprint of gravity waves on this that Brian Keating was talking about. And that takes you back here. Okay, so you have this black hole that may create a new universe somewhere else. Okay, Now the fun begins, because there are all sorts of possibilities. For instance, the possibility that all sorts of new singularities are created. Where's the room for them? That's where your other dimensions come in. And Andy spoke of the possibility that I wrote a short story about called What Continues, that is just incredible, that Lee Smolin came up with. And that is that if black holes, now try to follow this, if black holes create new universes, all right, then a universe that creates a lot of black holes is creating a lot of daughters. Now, all you have to do is add a couple more features to that. The physical laws of a universe are like its DNA. So if the baby universes inherit the physical laws that allow stars to form and all of that, so that you make black holes, then they'll have more babies. Now, all you need is one thing, a little variation in those laws. What have you got? Somebody. Evolution. In other words, those universes whose physical laws are just right so that it makes a lot of black holes will have a lot of babies. If their babies inherit this trait, those whose variance made it even better for making black holes will have more babies than those who didn't. You evolve universes toward the laws that will make more baby universes. Is your mind blown? This is so cool. Now, there has been an argument against this in that you could imagine physical laws that would make black holes a lot more likely. Why make galaxies? Because 99% of the stars don't make supernovas and don't make black holes. And I thought about an answer to that, and that is that maybe it's not just black holes. Maybe the black holes have to be tuned somehow. Maybe you need intelligent life, in which case the parameters are not optimized just for making black holes. Then the parameters are optimized for us. Well, it's an interesting concept. In any event, there's more. Oh, yeah, I was going to talk about evolution. Yeah, and evolution to the ability of us to be able to tune the process of making black holes. Here's another one. Are we all holograms? Well, mathematically, just in the last 15 years, it's been figured out. It's about 15 years, isn't it? Since this result. The turn of the century was really something. Way back in those days, the whole notion that you can mathematically connect our three-dimensional universe and all of its atoms and all of its quarks to the surface of a singularity like a black hole, which means that the hologram that's on a surface surrounding an area of space could be all there is, because that's all you need to describe all of the things going on. We all may be two-dimensional holograms, and I don't know where to take that. But some of you Clarion kids might. Brains! Those of you who watch Brian Greene's The Elegant Universe, you've seen some of these illustrations. The notion in string theory that our universe may be this slab, in many dimensions, but the metaphor is that it's, two-dimensional slab, containing all the vibrations in all of our galaxies, and they could be stacked next to each other like sliced bread. In which case, the notion is that this explains why gravity is so weak, because gravity is the force that actually can escape from the brain, whereas electromagnetism is constrained to the brain and constrained to our three dimensions. But here's the interesting thing. If you have a whole lot of these brains, then the notion is that some people feel is that if two brains connect and slam into each other, it creates a new Big Bang that sends them apart again. And then in both of those brains, you have a new Big Bang that destroys everything that's there. Now that's kind of disturbing. At any given moment, the brain next to our brain, which we cannot detect, heck, I can hardly detect my own brain, may collide with our universe and end everything and have another Big Bang. Well, that's kind of disturbing. I don't think so, but in any event, then you have quantum. Andy talked about this. He showed this slide of Schrödinger's cat, where in one reel, the radioactive particles decay and release poison, and the cat is dead. In another universe, the radioactive particle does not release the poison, the cat is alive. I think there's always a third in which the cat is extremely pissed off. But this is the notion that we make life decisions, and if only I had made my life decision otherwise, I would be happy with kids. Just go ahead and have kids and see how you feel about that. But yes, all the possibilities that branch off, and some wonderful sci-fi stories have been written about many ways that this could branch off. For instance, Larry Niven's All the Myriad Ways, and Robert Sheckley's The Store of the Worlds. I want to get to the art now for just a second, because what wonderful, wonderful theatrical art could be made with the just dramatization on stage of the meeting of two different versions of yourself, the different versions of what you might have been. If we could find somebody who looks a lot like Sheldon, we could actually have Sheldon come out with no shirt. and then someone else who looks like Jesus saying, boy, if I had time, you must not be a success because you've had time to work out. Here's another set of twins. Some of you may recognize these twin brothers. The Benford boys, Greg and Jim, they're mirror twins. One is left-handed, one is right-handed. One has a mole on the left side, one has a mole on the right side. One of them became a theoretical plasma physicist in the universities. The other became a theoretical plasma physicist in industry. So you see, there's divergence. But the question of what else might I have been? What isn't this a fundamental human theme and archetype? And this is one of the reasons why I'm putting out a call for San Diego sets of identical twins. Because they were the perfect actors for any of you who are playwrights who might like to work with the three of us. And our aim is to try to come up with, I think it's November, is it? Or sometime this winter, maybe next spring, some kind of dramatization that would include music or dance or any of the arts on this, one of the most spectacular of all themes, the question of multiplicity of paths, the multiplicity of possibilities. As the poet once said, I the less traveled path took, and that made all the difference. And then there's the question of simulation. Are we in the simulation? Well, that's the last of the categories of possible alternate worlds. And it's hit into the big time in sci-fi, the whole matrix notion, the notion that what you're seeing around you is not real. It's a basis for the godlike power that our children get from all the games they play, where they get to experience what previously was only experienced by crazy people, street corner preachers, and sci-fi authors, and that is the ability to be the creator of a whole universe. Well, the question then is, how do you know we're not in a simulation? And many of us have been writing science fiction about this lately. I have at least half a dozen short stories dealing with the question of, and some of them available on my website, the question of how do you know? How do you know that you're not in a simulation right now? Well, there are a few pieces of evidence that suggest that we are. If you were making a simulated universe, you would want to save on your computational power. So, one way of making sure that you save on your computational power is to make sure that your civilization doesn't deal with other species and other planets and other worlds, because that would have more to have to simulate. If you're going to simulate humanity, you want them cut off, as we are cut off from the aliens that we think ought to be out there. So what you'd do is you'd make the distance between stars really large, and you'd have an upper speed limit called the speed of light. And that would save you vast amounts of computational power. Another is you'd have an absolute lower limit to the size and that you can measure, the uncertainty principle. And that way you save on computational power also by the fineness of your mesh. You'd have a bottom temperature. There are lots and lots of weird aspects to our universe that make it seem as if it might be. But beyond that, what if we could physically make universes? Now you're talking the arrogance of Western civilization. Take it to its limit. And yet, there are religions on this planet that believe that co-creation is part of why we were made. It's why God, in the only pure moment in the Bible, asked Adam to name all the beasts, an act of co-creation. It's why in the Tower of Babel story, God says extremely clearly, nothing is beyond them. And if you look to the Baha'i people and Mormons, this is a perfectly natural part of growing up, that this is what people do. This is what the creations do, is that they become creators. And there are some in the Talmudic Jewish tradition who also believe this. So I just want to finish by saying that, saying up yours to Walt Whitman. He wrote a poem that was one of the most scurrilous and nasty and awful things ever written, and that was The Learned Astronomer. Did anybody ever know that one? Where he attends a lecture by an astronomer, and he sinks into a deep depression over the charts and the experimental results. And he goes outside and feels better by smugly knowing how much better he is than the astronomer, because he looks up at the stars in wonder. That's called the zero-sum game. In order to achieve the wonders that things like that Brian and his colleagues are achieving, and Andy, we have to surrender something else. But that's not the proper American attitude, at least. Not the proper human attitude, which is a positive sum game. I can have it all. By understanding the universe better, we can appreciate it better. How many of you feel, listening to the three of us, that we have lost our sense of wonder? Our sense of the ability to appreciate the beauty in a rainbow. All we're doing is looking at more rainbow. You are the kind of people, I don't have to lecture you about this, you're the kind of people who came here tonight. And that's really in all the cosmoses, the multiple layers of world, cosmos, universes of universes, that's the wonder. You. Thanks.
Maybe we'll address that to Andy.
Yeah, can you hear me? The idea is this is all just part of the same larger space. So that there's a sense in which these universes, even though they're so far away that we couldn't access them if we traveled at the speed of light forever, according to relativity, they're still connected. They're still part of the same larger space. And the idea is that we're still talking about the same laws of physics. So quantum mechanics, the same physics that governs inflation, would be in place in between these different bubble universes. And that but in each of them, observers from the inside, after inflation stops, would see what looks like a normal kind of expanding universe like we see. And the parameters of nature could be different in each of these bubbles. But the idea is that the laws of physics, you can distinguish between the laws of physics, which is what the equations look like, and then the parameters, things like these dimensionless constants of nature, like the mass ratio of the proton and electron. Those kinds of things could be different.
Yeah, the notion of an underlying context of laws within which, say, for instance, this evolution has taken place. Back 20 years ago, I was asking this question, of some of the physicists who were still saying the expanding balloon is all there is, and the laws all began at that first moment when it all emerged out of a fluctuation in Heisenberg's uncertainty principle. And I said, yes, but in which context was there a Heisenberg's uncertainty principle? And now the notion is that there are some things that pervade whatever metaspace is there, that allow then each cosmos to have its own details.
Okay, thank you guys. Where's the microphone next to? Okay.
Brian, you've talked about the discoveries of empirical evidence through cosmic background radiation, gravitational waves of the Big Bang. What physical evidence might we achieve someday to demonstrate the reality of multiverses?
Yeah, so there are different classes. So the question was what other types of empirical evidence might prove or motivate the fact that there might be indeed a multiverse. So there are different levels of predictions and models that predict startlingly obvious signatures. David actually showed one where you have these two circles on the sky in opposite places. And people have looked for that, those signatures in the cosmic background radiation as well, seeking to perhaps detect the collision between two of these baby universes within the multiverse. So that's perhaps one of the most obvious ones. Then there are different levels of credulity if you're willing to accept the notion that a discovery of gravitational waves proves or motivates inflation, and that inflation must be difficult, if not impossible, to stop, that it must be going on everywhere. So even though we might not detect these other universes, similarly, we believed 100 years ago that atoms were the most finely grained substance that we could possibly detect and observe, and the laws of nature were as we knew it back then. Now we know much more. So I think we'll winnow down the possibilities first, and then we can delve into potential other observable signatures. But I should say that it's motivated equally well from inflation theory and string theory, and I don't know of a way observationally to prove it from the string theory side.
There are some ideas, very speculative, in these versions of string theory where you have these large extra dimensions, like these brain world scenarios that David was mentioning. We have some evidence that's very intriguing. This is the idea of so-called dark matter. It seems like there's a lot of missing mass in the universe. And some people speculate that one way of explaining this is that it could be due to the gravitational influence of other brains farther away. I don't know if this is correct, but that's the kind of a thing where maybe there actually already is evidence out there for other universes, and we just need the theoretical and philosophical framework in order to really elucidate that.
Yeah, I think the notion that there might be brains next to ours, we already have as one of the theories that gravity can leave our brain, whereas some other forces can't. In which case we might be feeling another brain above, another below, and wouldn't they cluster their galaxies near ours too by the gravitational influence? And this would explain some of the effects that we see in our galactic rotation. If I might also add, those of you who are artists, I didn't mention it, if you're interested in pursuing any of these ideas for possible performance art about the multiverse, get in touch with Sheldon Brown or any of us, care of the Clark Center.
Yeah, great. Can we move the microphone around throughout the room, please? Okay. We'll start over there. Yep.
Hi, and thank you very much. I thought this was all fascinating. I have a question. I've been studying this for about 30 years, and I'm just wondering if any or all of you may have looked at this from a slightly different direction, which is basically from the direction of the golden ratio, the Fibonacci sequence. Having looked into that, I found it fascinating that just about everything that's considered beautiful or balanced is based on that ratio, about 1.61 something. And the more I looked into it, whether it's the arrangement of the pistils of a sunflower, or the curvature of the nautilus, sea nautilus, or the curvature of the human ear, or the spiral nebula that you look into, or the curvature of a wave, all is built on this same ratio throughout nature. And I think in 2003, which is where I'm going with this, if I'm not mistaken, French cosmologists had deduced that the actual shape of the universe was a dodecahedron, which again is built on this same ratio, which you would think is an artificial shape. So in getting into multiverse theory, I'm wondering if you've looked at that ratio, what role it could play in all of this, and having a descriptor for what this all looks like and how it fits together.
I have not looked at that. I don't know. Have you guys looked into that?
Well, it occurs to me that we like it in part because we're constantly perceiving us around us, and that natural phenomena that are additive processes, like the creation of crystals, the creation of branches on a tree, that these would tend to follow a Fibonacci sequence if they're adding in a relatively moderate way. So it may be, it's just the matter that when nature adds things to adding things to adding things, that it occurs a lot, and we find it pleasant because it means that whatever's going on is healthy. That's just a speculation. That's just a sci-fi.
And one quick follow-up question to that is that I don't know if any of you have seen I think it's a somewhat famous picture on the internet, but they did a slice of a mouse's brain and illuminated it, and then they overlaid a picture of the universe, and it was nearly identical.
Well, one of the things that's been out lately is if you take a look at the Sistine Chapel, and if you look at the funnel, singularity hole, that God is emerging from with his cherubs, with his hand to give the spark of life to Adam, it's shaped exactly like a human brain, with the filigrees coming off exactly where the cerebellum is, and his hand coming straight out of the prefrontal lobes.
Interesting. Yeah, my student John Kaufman. Thank you for the question. My student John Kaufman is a student of this type of art in the microwave background, and he actually found a very distinct picture of a rabbit in our data set. It's quite beautiful. Can we pass the microphone around? Cosmic rabbit hole. Maybe in the way back. I see someone who's had her hand up for a long time.
So if there were specific requirements in terms of the constants and the laws of physics that were required for life to begin in our universe, and there are also other multiverses where laws are different, how could other universes support life?
Maybe Andy, you can address that.
So we really don't know very much as we would like, about how likely life is to come into existence. What we can say are things that we think are crucial prerequisites for our kind of life. And you can make some pretty plausible arguments for what are the kinds of prerequisites you need for life in any case. For example, you can have parameters like of cosmology where the universe collapses after a fraction of a second. I don't think anything's going to happen very interesting there. And you can have the universe expand and accelerate so fast that everything just becomes empty and all the matter is diluted. I don't think things are going to happen there that are interesting. So it could be that if you looked at this whole multiverse, by some measure, most of the universes are really uninteresting from our perspective. Maybe most of them don't have life at all. And so this is still an open question. We actually really don't know how to do statistics, especially. Oh, go ahead.
Could there be other universes that don't necessarily support life but have things like similar solar systems, planets, stars in the same kind of way that we do?
It's certainly a possibility. Because we have a real lack of knowledge here, we know things that are necessary conditions for life, like having a planet, but we don't know what the sufficient conditions are. So we don't know how likely it is for life to start, for evolution to get going. I personally think it's quite plausible that you could have a universe with planets, but life didn't evolve. It really depends on the answer to open questions which we don't understand about how likely it is for self-replicating molecules to kind of get going.
Yeah, what you're talking about to some extent is what's called the anthropic principle. And that is, it's no coincidence that we observe that we're in one of those universes that had the conditions necessary for you to have life. Because nobody's in those other universes to notice that they're in a sterile universe. What the mind then starts doing is saying, what's the ratios? Are there gazillions of sterile universes for every one that gets people sitting on stage asking silly questions about parallel universes that they're never going to see anyway? Well, that's where Lee Smolin comes in. Because if there's evolvability of universes and this multiplicity of universes, the laws aren't random, but they're inherited and refined by evolution, then the vast majority of our sister universes have fecund life in them. And a majority of them have at least some bipeds in auditoriums talking about this. And if you dispersed it out across the infinite space, some of those bipeds will be wearing mostly black and answering questions from somebody wearing white.
Thank you. I can't, maybe we'll move it up somewhere in the middle there, but I can't stress enough, no matter how long our universe may last, or our multiverse, you must keep paying your taxes. I think right over there.
Yes, I wanted to say something about the anthropic principle. It's always described in terms of very narrow tolerances on any one parameter. But Victor Stenger, among other people, have shown that if you vary several parameters at once, you may get very strange universes, but they still have complex matter, or should. And also, there's actually another paper out with describing a possible universe with complex matter, and there's therefore possibly life, that doesn't even have a weak nuclear force. So I think that the range of variation is really much wider than most people think.
Oh, well, even if you have even if you have a universe where it's hard to have a Goldilocks zone, these Goldilocks zones that Andy showed, around stars, perfect for water on the surface of a planet. We now realize that it's highly likely that there are oceans still in the universe covered with ice, worlds like Europa and Enceladus. We now believe that there are as many as a dozen worlds in our solar system that could be abodes for life because they have liquid water under conditions that have some energy. So even if the Earth weren't here, which means that almost all of the solar systems probably have some, even if the star is not stable, even if there's no Goldilocks zone, if matter condensed and there's a snow barrier and there are ice worlds, there's probably something that could have life in almost any solar system.
Yeah, this is a very, very good question because we don't know enough about the conditions that are necessary for life to know whether or not there could be other islands in the parameter space of the multiverse where very different kinds of life could evolve. I think we need to exercise due humility here and recognize that we don't know what would happen if you change multiple constants at the same time. People like Victor Stenger and others are just starting to think about this. It's definitely an open question. These are why these questions are so exciting. There's so much more to do.
Of all the exciting photos that I've seen, the Viking lander and so many others from our space program, the thing that jazzed me the most was the image of an ocean, shoreline, clear river patterns, mountains on Titan. The Huygens space probe showed what are clearly oceans of methane and gasoline and mountains made of wax overlying ice. I mean, if there are living beings there, they would be made of wax. And some of you in this room, will live in a civilization that actually goes there and finds out. I'm hoping almost all of us.
Okay, so maybe we'll take one more question.
This guy's had his hand up.
Yeah,
relentlessly.
let's bring it up front and then him, we'll finish up.
Hi. So, talking about the universes inside black holes or being created by black holes, if that were the case, and our universe were inside a black hole, or any universe like that, wouldn't there continually be more stuff in the universe? Like it would be expanding, but not only adding space, but matter as well that's coming through.
As well. Yeah, Andy, you want to tackle that?
It's an interesting question, what the relationship is between the inside and the outside. And there's a certain question, it could be very, very much that we were kind of screened off from anything that's happening outside. In the cases where a singularity is formed and a new sort of universe, pinches off, the relationship between the parent and child might end. So in that case, you might not be dealing with an influx of new matter. Let's say there are other more complicated ways that space-time can be intersecting, like wormholes. It very well may be that if stable wormholes exist, then indeed you could see an influx of matter going through from a distant part in space and time. And if you're asking the question about our universe, we certainly don't see evidence of giant agglomerations of matter appearing out of nowhere. Maybe that, if we're inside of a black hole, we're not necessarily, at the other end of a wormhole. But these are all very interesting open questions, and it's certainly a fun and exciting thing to think about. And it's actually amazing that you can think about these things, and then you think, okay, wait a second, how can we experimentally test for the existence of wormholes? Particles of matter would be traveling in slightly different ways around wormholes than around normal black holes. This is something that astronomers might eventually be able to detect. And if those are detected, not only would that be Nobel Prize winning, it would be the kind of a thing that would allow us to realize that some of these places, which seem inaccessible forever, are actually not necessarily in principle inaccessible. I certainly hope that the universe ends up being a place where the ideas we can think of are also ideas that we can test. And that's an aesthetic bias. I don't know if that'll be borne out, but it certainly would be a little bit more kind if the universe wasn't playing a cruel joke on us, that we can think of these things.
So let's all turn to the simulators who are running this simulation
and thank them
tell
very
them,
much.
Hey, how about it here?
Thanking our sponsors.
Always turn to the third wall all the time, because that way you can tell the simulators, I know. And we never got around to much about theology, but that's another time.
So see you all on August 11th for the next SciFlix movie and next Arthur C. Clarke Center for Human Imagination event. Thank you all for coming.
Thank you. Thank the panel. Thank you very much, guys.
Good work.
Yeah.
A lot of fun. It was great.
It was terrific.
Yeah.
Don't take the microphone. Keep it up.
So,
Done that before.
did you ever?